So as is usually the case, talking about the idea of something, it helps to understand. But for me, it always came down to when I saw it used in a problem, I kind of got a better feel for what was going on. And so I like to give examples where I can, and we'll use this one as an example. Energy is your friend. So when you have this kind of problem, you should recognize by now, whether it's rolling or not, something moves, whether it slides or rolls up an incline like this, and you see a change in height, alarm bells should be going off about mechanical energy. And that energy is going to be by far the way to go about doing this. So what is going on here? Well, I think of energy in this case, I think of the mechanical energy initially and the mechanical energy after going up the incline have to be the same, because everything's a conservative force. In this case, it went up, gravity was the force that would have slowed the kinetic energy down, or slowed the velocity down. You'd move some kinetic energy and turn that into potential energy. But the total mechanical energy is going to be the same. Now let's take a moment. The number of people that have been invited to this mechanical energy party is increasing. I mean, if you think about it, a while ago we discussed mechanical energy. It was just the kinetic energy of the object plus the potential energy of the object. And at one point, all we knew about was gravitational potential and what we call now translational kinetic. But there's a lot more to this now. We have to expand this out. Mechanical energy, when we talk about kinetic energies, there's two flavors. There's two types. You can have translational kinetic energy, 1/2 mv squared, or in addition to, you could have some, possibly, like in this case, you could have rotational kinetic energy. The fact that the ball is spinning as it moves. It's in rolling, which is the combination of spinning and translational. And, let's see, potential energies. Well, there's gravitational potential in this problem. And not that it pertains here, but the other potential we picked up along the way was the potential energy in a spring. So, in this case, obviously, we could ignore the spring. There is no spring in this problem. But it would be interesting maybe if it hit a spring here, and how far would you compress the spring, blah, blah, blah. You could introduce one. I'm not sure how you'd handle the rolling part. I have to think about that. But for us, we have to consider three forms of energy that are now under the umbrella of mechanical energy. But either way, this is definitely no friction involved or anything like that. This is definitely a conservation of mechanical energy problem. That is going to be true. Now all we got to do is figure out, put all the pieces in place, and hopefully there will be a bunch of stuff that cancels out. Because if you're like me, you look at this problem, they only give us the height that it rises and the initial speed of the ball. Translationally speaking, they don't give us the mass of the ball, the radius of the ball. There's a bunch of stuff they don't give us. In these situations, it's best not to panic. Just go with what you know. So we've established that the mechanical energy is conserved. And we know that mechanical energy consists of these, in this case, these three quantities. Let's not overthink it. Let's just go with what we know. That means that the initial mechanical energy would be the initial translational kinetic energy. Notice a little zero there for initial, for when time was zero, for the start of the problem, however you want to look at it, plus the rotational kinetic energy that it had initially, plus the gravitational potential energy it had initially, which, yes, I know you're thinking, zero? Yes, it's going to be zero, because initially it was down here, equals the final translational kinetic energy plus the final rotational kinetic energy plus the final gravitational potential energy. Now, we will just jump to, not jump, but we will realize that we're going to have h equals 0 here. So this we can just take away and call it 0. But before we start plugging in other variables, velocities, omegas, i's, all the other stuff that we have to worry about, let's consider this a little more conceptually for a while longer. So you have the kinetic energy, translational kinetic energy it has initial, plus the rotational kinetic energy it had initially. So as it was coming down the lane, it was both spinning and had translational motion. It had energy. And it had those two types of energy. Those two types of energy, presumably, well, they're connected, by the way, right? There's a connection between the velocity of that center of mass and the angular velocity, are connected to each other. So when the ball slows down going up here, why did it slow down? It's going to cash in some of that kinetic energy for potential energy. So whatever kinetic energy, just use that as a general term, both of them combined, whatever kinetic energy it had here is going to be more kinetic energy than it has here. By how much? Well, by whatever the potential energy increase was. So in other words, if you know this and you take away the potential energy you picked up, you're going to know the kinetic energy you have here. So that's the general idea we're going to work with. But let's continue this expression. So we don't have potential energy at the bottom. Kinetic energy translationally after it goes up the incline, plus the kinetic energy rotationally after it goes up the incline, plus this potential energy that it has picked up. And like I mentioned a moment ago, right now I'm going to subtract this from both sides. Because I know how fast it was going in the beginning and its height and everything. I know this stuff. Whatever that total kinetic energy was, minus this, should be the kinetic energy I have afterwards. So I'm just going to rearrange this at this point. If you don't, it's not the end of the world. I just think it's going to be a little more helpful down the line. Translationally final plus the kinetic energy rotationally final. If you try to do this in the margins of your paper, you're going to get confused and you're going to have a problem. It's this type of problem, it's going to baffle you. You got finals, initials, you're going to lose track of them, and things are going to get ugly fast. So that's my warning to you. Say it almost every time we do one of these. So I think it's time we actually put in some of the players here. So instead of just writing kinetic energy, let's do this. We're going to write, all right, 1/2 mass of the bowling ball. I know I don't know it, but you probably can guess what's going to happen to that, times the initial velocity, translationally, of the ball squared, plus rotational kinetic energy. Well, we're going to have to deal with this one for a little bit, but we're going to write 1/2 the rotational inertia of the ball. We can go look up that formula in a minute, but we're going to have to. But for now, just rotational inertia of the ball times the initial angular speed of the ball squared, minus the final, so mgh, final. But we'll just use h because that's the height it went to, equals 1/2 mv final of the ball squared plus 1/2 I omega final, it's not spinning as fast now presumably, squared. All right, so which one you want? Well, there are some things in here that we definitely did not get handed to us. There's a lot of things in this problem. If you look at this problem carefully, they didn't tell us the mass. They didn't tell us, they didn't give us a number for this. They didn't tell us this. So there's a bunch of things in here that, and of course I don't know this because that's what I'm looking for, but there's a bunch of stuff they didn't give me. But all of it is going to divide out. But we have to expand some of this stuff. We have to deal with this. Well, I guess we include the square. But we have to deal with that. So let's deal with I first. I first? Yes, let's deal with I first. So what is I? It's the rotational inertia of our ball. And the ball didn't change shape or lose mass or gain mass, so this I and this I are the same. Bowling ball. Basically, except the little holes for your finger, we can ignore those, they're small enough. Bowling ball is a solid sphere, and it will be rotating around its center. So, right here, solid sphere, rotating through its center, 2/5 mr squared. right there. That's our guy. So, I know that for a solid sphere, rotating about its center, it's the mass of the ball, radius of the ball squared. I'm going to plug that in right now to the two places where I see an I. So I'm going to have 1/2 m v initial squared plus 1/2 times 2/5 times the mass of the ball times the radius of the ball squared times omega squared, initial angular velocity. So all I did was replace I. And in fact, you know what? We don't need, let's clean this up a little bit. We don't really have to have these parentheses. The 2/5 and 1/2 will be a little weird, but you'll see in a moment we're going to take care of that. So I'll just put a little dot here for that. There we go. We'll get that. But all these quantities here are just being multiplied times each other. Minus mgh, that doesn't change. Equals 1/2 m final translational velocity squared plus 1/2 times 2/5 times mr squared times the final angular velocity squared. Okay. By the way, we've entered the world where I'm teaching you algebra stuff, not really physics, but that's okay, because it's helpful. You're going to need it to get through stuff anyway. I got two things I want to point out. One of them, hopefully, is pretty obvious to you right now, and that is that by introducing I, which has an m in it, right, has the mass of the ball in it, that all of these masses, since every term has a mass, as is always the case when you have a situation where an object, where gravity is the thing doing the accelerating or decelerating in this case, there's masses. That's why they don't give it to you, because they're going to divide out. And the fundamental idea here is, like, if you dropped a bowling ball and a ping pong ball, the mass of them doesn't affect the acceleration. So remember that so therefore it shouldn't affect this either. So the masses are gone. And here's the other thing I'm going to do. I don't like dealing, I'm going to try to avoid dealing with fractions as much as I can. I'm going to multiply. There's a few ways we can do this. Let's do this. I'll get rid of these fractions. I'm going to say 1/2 times 2/5, first of all, is 1/5, correct? You cool with that? That's going to be 1/5. I'll just do that now. And this is going to work out to be, right here, is going to work out to be 1/5 as well. But I don't want fractions. So I'm going to do a little trick. I'm going to multiply every term here. I'm going to multiply this, 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 and this by 10. Why 10? Because it's a number that both 2 and 5 go into. That gives me 5, right? 1/2 of 10 is 5. I don't have the m anymore, right? Don't forget that, Wellborn. You got rid of the m. So you got 5 VO squared plus 2. I did the m again, too. Canceled that, right? You saw me do it. What am I doing? 2 r squared omega 0 squared, original squared, minus 10 GH equals 5 V final squared plus 2 r squared omega final squared. Now I don't have fractions to worry about. Makes things a little easier in my head. So, almost there. Got a couple more things we got to do. I don't have anything about omega, but you might remember from earlier videos and from me mentioning a moment ago that there is a connection between the velocity, the translational velocity, and the angular velocity. And that connection, as it often is, as always is, in terms of rotational motion, is the radius. You're like, I don't have the radius. Chill. I got you. Don't worry. You can probably see it happening here. So I'm going to replace this. Now, if I have V, center of mass, equals R omega, I'm going to solve for omega. So that's V divided by R equals omega. So I'm going to replace this as follows. 2 times R squared. Omega is going to be V original, the original translational velocity, divided by the radius, that whole thing, squared. Minus 10gh equals 5v final squared plus 2r squared. What goes in here? Using this idea, but using the final situation, I'm going to final velocity over the radius of the ball squared. Now, when we square this fraction here or over here, all I do is square the top, the numerator and the denominator, the top and the bottom. So really, I can dump that, and I could just write that squared over that squared. Same thing over here. Saving myself a step from rewriting the whole thing. What do you notice? If you look at it carefully, you should notice that your radius goes away. Turns out it doesn't matter how much the radius of the ball is either. Mass doesn't matter. It could be a small, small radius bowling ball or a large one. It could be a golf ball going up there for all we care. So, interesting. Now what do I have? Well, I have, let's clean it up, 5VO squared plus 2 times VO squared minus 10GH equals 5V final squared plus 2V final squared. Oh, wait a second. I can just combine those, or these, because it's the same. So 5VO squareds plus 2VO squareds, I have 7 original velocity squares. Minus 10 times GH equals 7 V final squareds. But I'm looking for that V final. So if I do 7 times the V original squared minus 10GH divided by 7, that'll equal V final squared. And if I want to get rid of the squaring, I square root. So I'm going to do the square root of both sides. And that's going to give me, my V final is going to be the square root of 7 V original squared minus 10GH over 7. I'm going to give it a shot, see if I did it right. Let's find out. So I believe I have the following, without scrolling up, which I do it from memory. I have 7 times 5 point, no, I can't remember, 2 or 7, one or the other. 5.7 squared minus, what was the height again? 0.70760? Minus 10 times G times H, which is 0.76, all divided by 7. And let's see what we get. So 7 times 5.7 squared, it's 227, there it is, 0.43, minus, let's see, 98 times 0.76, 74.48, divided by 7, and then take the square root. Careful how you do all this stuff, but let's see. And then divide by that 7, and then take the square root. And I get 4.67 meters per second, which I believe, there it is, Okay. I haven't lost my touch.